Okay, so in your notes, you'll see charts that look like this. I'm going to try to explain to you a little bit about what this is. The bottom should be making some sense to you at this point because you have a position time graph, and when you take the slope of it, you get a velocity time graph. You have a velocity time graph, and you take the slope of it, you get an acceleration time graph. And then the opposite of slope is area. So if you have an acceleration time graph and you take the area, you get a velocity time graph. If you have a velocity time graph and you take the area, you get a position time graph. The top of this page, though, may be a little more confusing. And what this says is that if you have in the first line, if you have a line that is curved, like these here, and you take the slope of those lines, you get diagonal lines. If you have diagonal lines and you take the slope of it, you get a horizontal line. And if you have a horizontal line and you take the slope of it, you end up with a value of 0. And just like in the problems at the bottom, the opposite of slope is area. So you end up with the area giving you the values of a horizontal line. Take the area, you get a diagonal line. You have a diagonal line, you take the area, you get a curved line. Here are some examples of what this looks like. So here I have a position versus time graph, and I'm trying to draw a position versus time graph from a velocity versus time graph. To get a position versus time graph from a velocity versus time graph, I need to take the area. So in looking at the first graph up here, I have an area in the first second of 1.5 or 1.5. In the next second, I have an area of 1.5. In the next second, I have an area of 2.5. In the last second, the second here, I have an area of 3.5. And this is coming from if I were to break down this graph into increments. So I have a triangle, then I have a trapezoid, then I have another trapezoid, and then I have a last trapezoid. So the area of each of these trapezoids are going to be 1/2, 1.5, 2.5, and then 3.5 in that last second. So the area under a velocity time graph becomes the change in position for the position time graph. So if we assume we start at 0, in the first second, we go 1/2 meter. In the next second, we go 1.5 more. So I go over 1 second, I go up 1.5 more. In the next second, I go 2.5 more. So 1, 2.5. In the next second, I go 3.5 more. So 1/2, 1.5, 2.5, 3. And so you end up with these points, and when we graph them, we see that we are getting a parabola. Remember how we started this. We said if we take the area under a diagonal line, we end up with a curve. Let's go back down and see that. If we take the area under a diagonal line, that's right here, take the area under that diagonal line, we end up with a curve. And the curve we ended up with this time is the first one. Depending on the slope of the diagonal line, depends on what type and what the initial velocity is, determines which one of these curves you get. But you know that when you are going to take the slope of a changing velocity, and that's what we are looking at here, a changing velocity, you are going to get an exponential change in the position. Now, to take the slope of the diagonal line, the velocity, when I take the slope of that, I get a value of 1. It's a nice horizontal line through 1. And the slope of a velocity time graph is acceleration. The area under that velocity time graph is position. And so we can see that the slope of a diagonal line is a horizontal line. Let's see down here in our chart. When we scroll down, we can see again that when we take the diagonal lines and we take the area of them, we get horizontal lines, nice horizontal lines, which is exactly what we originally thought should happen. Now, so back up at the top here, we have in the second graph a horizontal line. So the area under a horizontal line should be diagonal, just like the area under the diagonal line was curved. And so when I am looking at this, and if I break it down into individual seconds, I have 2 for the area, 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 which means that as I'm looking at this, remember when I'm going from velocity to position taking area, I am saying that in the first second, my y value changes by 2. In my next second, my y value changes by 2. In my next second, the y value changes by 2. This is going to continue to happen, and so I get a diagonal line. In the bottom graph, where I'm finding acceleration from velocity, I'm taking the slope. The slope of a horizontal line is 0. So that means that on the acceleration graph, I am going to have an acceleration graph that is just along the 0 axis. The trickiest of them comes with this velocity graph at the end, because the velocity graph has a horizontal line that is 0. The slope of 0 is 0, so it would have 0 acceleration. That makes sense. But the position graph, a horizontal velocity of 0, does not tell me where I have started. If I start at 0 and I have a velocity that's staying 0, then the slope of that is 0 and the position would be here, but we aren't sure of that. There could be a different start point. If there's a different start point, then we would have a horizontal line wherever that start point is. I personally will not be throwing anything like that at you, but that is something that you will talk about more in some more advanced math classes. For this class, if you understand the concept that the slope of a diagonal line is going to give you a horizontal line, and the slope of a horizontal line is going to give you 0, and then backwards from the slope of the area under a horizontal line is going to give you a diagonal line, and the area under a diagonal line is going to give you a curved line. You should be okay. If you have any questions, please let me know.